Hi, welcome to Scientific Knowledge is Imperfect but Powerful, a user's guide. Let's start by stating the problem. On the one hand, there are laws of nature that determine how the universe works. These laws determine how stars and galaxies work, how viruses work, and how ducks work. On the other hand is our understanding of those laws. For example, we can write down Einstein's equations to describe gravitation, equations describing the emission spectra of atoms, and the relation between energy, momentum, and mass in the theory of special relativity. Also, we can make models of natural phenomena, so we can write down a rudimentary model of how a duck functions. But the laws of nature that determine what happens in the universe and the laws that we write down are not the same. Why is this the case? Well, let's discuss two reasons. The first is that when we attempt to describe some phenomenon in nature, we do simplifications and leave out some information to make problems tractable. The second is that there are effects from principles of nature that are still unknown to us. Let's look at a couple of examples. For the first example, let's look at a system commonly covered in high school physics courses, a mass on a spring. Okay, so we have a spring, here hanging from a horizontal surface. At the bottom is a purple ball. The spring can stretch and contract, moving the ball up and down. When the spring is left to hang and is not moving, the ball will be at a certain position. We define this position as x equals 0. When the spring is stretched or compressed, the ball will be at a different position, which we will call x. To describe the force on the ball as a function of the ball's position, we write down the equation F equals minus kx, where F is the force on the ball and k is the spring constant. But there are a lot of details left out of this description. For example, air resistance. And the spring itself isn't a perfectly homogeneous object. Different parts of it will have slightly different stretchiness. For that matter, the spring itself is a huge, complicated system of interacting atoms. Also, this model will fail badly if the spring is stretched too far, and so on. So, in this example, it is clear that simplifications have been made in the description of this system. We know that there are effects from known principles that we have left out in order to make the problem tractable. We don't know the exact size or even necessarily the sign of these effects. We might know their approximate size, or we might know that they are small enough for our purposes. If we did know the size of these effects, we would include them. Well, we would if they were large enough to matter and didn't make the problem intractable. Okay, so what we see here is that the law we wrote down, F equals minus kx, does not perfectly reflect reality. There are physical effects that have been omitted in this description in order to simplify it enough that we can use it. This means that the laws and models that we wrote down cannot perfectly reflect what the universe actually does. Okay, let's look at example 2, Newtonian mechanics. Newtonian mechanics, of which we just saw an example, is typically taught in an introductory physics course. But in the 20th century, we learned that Newtonian mechanics is not exact. In fact, if we do experiments under conditions that are very different from everyday life, Newtonian mechanics can be a very poor approximation to reality. For example, if we look at phenomena that involve speeds close to the speed of light, we need to switch to special relativity in order to get predictions that closely match observation. And if we go to very tiny scales, we need quantum mechanics. Newtonian mechanics is not absolutely true, but just an approximation to reality. At scales and speeds that are familiar to us, the approximation is excellent. So for a long time, it seemed to describe nature really well. But as experiments probed greater speeds and smaller distance scales, Newtonian mechanics was found to no longer agree with observation. The approximation failed. So, in this example, there were underlying effects from principles of nature back when Newtonian mechanics was formulated. We simply did not know. Since we haven't yet discovered all the principles of nature, there are always some effects like this that are left out of the descriptions of natural phenomena that we write down. Just like in the previous example, we don't know the exact size or sign of these effects. Or at least, since they are from unknown principles of nature, if we somehow do learn the sizes of these effects, that probably means we've discovered something about the universe. Now, we might know that these effects from unknown principles are small, from other experiments and observations that have already been done. Like in the previous case, if we did know the size of these effects, we would include them in our models and laws. That is, if they were large enough to matter and didn't make the problem intractable. So, in short, the laws and models that we write down have imperfections due to effects that we don't yet know about. Effects from natural phenomena that we don't know about yet will lead to our laws and models not perfectly describing reality. Here, we have looked at two examples and seen that our laws and models leave out effects, either ones we in principle know about or ones we haven't discovered yet. So in both cases, there are differences between reality and the laws and models we write down to describe it. Which means that either way, the laws and models we write down will make predictions which will not perfectly reflect reality. There are two ways of dealing with this issue. We can apply the models and laws that we have, taking the resulting uncertainties on their predictions into account, and we can make the models and laws that we have better. Both of these approaches are important and both are in the physicist toolkit. Critical to both of these approaches is being able to quantify uncertainty. We need to quantify the uncertainties in the predictions of our models and laws. And we need to quantify uncertainties in the results of the measurements that we make, because the results of those measurements are used to formulate our new, better models and laws. Here's the good news. We have tools to address these issues. Science has tools for quantifying the uncertainty on scientific results and quantifying the uncertainty on the predictions of our laws and models. The goals of this series are to understand why and how uncertainties arise, understand one of the main ways uncertainties are quantified, see how those uncertainties come into the interpretation of scientific results, see the role uncertainties play in the evolution of science, see how uncertainties play into modeling the world around us, and see how the same tools apply to everyday life.